Good morning, Eastview Scholars. Welcome to this edition of Sharp Shorts, where we're going to look at the relationship between percent yield, percent error, and how you use that with your stoichiometry in the lab. Obviously, the ability to use stoichiometry is to go into lab and accurately predict your product and make an exact amount of product. The percent yield or percent error tells you one of two things. It's kind of two sides of a coin. How close were you? How far away were you? So I have the definitions here. Percent yield, how much of the actual product did you make when you compare it to what you could have made? And here's the formula. The actual, which is the actual mass or experimental mass, depending on who you talk to and what books you read. But that's what you did in the lab. So I went in the lab. This is what I made. So you would have that number from getting the mass at the end of the lab. Or on a test or a quiz or a worksheet, you'd have to be told what that experimental mass is. You divide that by the theoretical mass. The theoretical mass is always the one you calculate from stoichiometry on paper that says, this is what I could make from a balanced equation, and then multiply by 100. Now I also have percent error on here because essentially they're two sides of the coin. Percent yield tells you how close you were to how much stuff you could have made. Percent error really tells you how far from 100% yield are you. Okay? And that's why the two add up to equal 100%. One is, how much stuff did I actually make out of what I could have made? The other is, how far off from 100% was I? Okay? And we've done percent error in lab. Again, it's an absolute value. You take the experimental mass that you got, subtract the theoretical mass, what I could have done that I calculated by stoichiometry, divide that by the theoretical mass, again the stoichiometry calculated one, absolute value, so it doesn't matter if it's negative times 100. Alright, let's just put it into practice. Here's my problem, and it looks like a mess, and part of the reason I use this one is that while it looks like a big mess because of all the carbons and stuff, if you balance this thing, the only thing you have to do is place a 2 right out front there. All right? Okay. So, and then the whole thing is balanced. This is something called chlorobenzene. This is called chloral. And this right here, the reason I put this out here, this is DDT. Back when I was a youngster 4 or 5 years ago, DDT got banned because while it was a very good pesticide and people would spray it on their plants and stuff and kill all the bugs and have pretty flowers and everything else with this DDT, it was also toxic. It stayed in the tissue, so the buggies would die and the birds would eat the bugs and the birds would die. And maybe the birds would, you know, and it just got into the ecosystem. Or maybe, you know, the birds are flying and they die and fall in the ocean and the fish nibble on them, then the fish are dying. But it was while it was a very good pesticide, the fact that it stays in tissues and builds up and kills the things that not very good. Anyhow, here's our problem. What we want to figure out is how much DDT do we make? Okay. And to do that, we're going to have to figure out which of these is a limiting reactant and which is an excess, so we only use a limiting reactant. And then in the end, what we're saying is we actually in the lab produce 950 grams. What is the percent yield? So we'll figure that out. Anyhow, here's our balanced equation. This is what we want to find out. First thing we got to do is divide 1142 grams of the chlorobenzene by 112, and that comes out to be 10.15 moles to 4 significant figures. Okay. Now, the chloral here, 485 divided by 147.5, that comes out to be 3.29 moles. On my glance, and sometimes you can do this, it sure does look like the chloral is the limiting reactant, but again, it's a 2-to-1 ratio. So really what I should do, as instructed in our last video, is divide each of them by their coefficient. Well, 3.29 divided by 1 is 3.29, and 10.15 divided by 2 is going to be 5. Oh, call it 5.075. So all that does is confirm for us that this is my limiting reactant. Okay. This is my excess reactant. So I'm going to have some extra chlorobenzene left over when this reaction occurs. Okay. What that means, though, is this is the one I need to use, the 3.29 moles here. Okay. Well, the nice thing is it's a 1-to-1 ratio, so you also have 3.29 moles of DDT, the deadly pesticide, in more ways than one. And that times that comes out to be 1,166. We should probably round it, 1,170. We'll just say 1,166 grams of DDT could be made. Okay? Now, my percent yield. What is my percent yield? Well, remember by the formula, it's what I did experimentally, which down here told me was 950 grams. Divided by what I could have gotten calculated in theory by stoichiometry, which is 1,166 grams. Apologize for my writing, the pen's going a little crazy. Times 100. Okay. So when I divide that and divide by that and multiply by 100, my percent yield, and you can do the math, but the percent yield comes out to be 81.5%. Okay? All right? Which means that you're looking at an 18.5% error. So this is not a great yield in the world of industry. There's a little bit of error, but that goes back to, you know, the fact that these are opposite sides of the coin. I had 81.5% yield, which is then 18.5% error. Okay. Now, that's one way to use the formula. The other way to use the formula is I could have told you that this reaction only went at 81%, and how much DDT will I make, in which case I would just plug in and solve the algebra for it. So that's another way to use percent yield, is to say, well, here's the percent yield that's going to occur with this reaction. You're only going to be able to do it at, say, X number of percent, 95%. How much stuff will you actually make in total? And then you can do it that way. But you have some of those problems in your packet, and I will let you go practice those. And our next video will be show what to do if you have a multi-step process. And then you should be all prepared for stoichiometry. Scholar up, Eastview.